working with Professor Sarah Wiley in the Department of Sociology on this project, developing a community-based DIY photo paper tool to visualize and map exposure to hydrogen sulfide, which is a toxic gas. And it's frequently found around oil and gas fields. So hydrogen sulfide, it's commonly called sewer gas or sour gas, and it's mainly produced by bacterial decomposition. It's naturally present everywhere at low levels, but considering that oil and gas are products of organisms that decomposed millions of years ago, it's commonly emitted during oil and gas extraction. It's also heavier than air, so it usually lies in depressions like ditches or valleys. It's often recognized by its rotten egg smell, and it's corrosive. Some health effects include eye irritation, damage to one's sense of smell, respiratory irritation, and at 750, 1,000 parts per million can result in death. So most of these are acute, short-term effects, but most scientific studies only cover these effects, not the low dose, long-term effects like chronic respiratory, neurological symptoms that community members often experience. So we developed this tool based on the fact that it's a corrosive gas. Hydrogen sulfide reacts with silver embedded in the layer of gelatin on photographic paper, and then it tarnishes it. So we can look at the level of tarnishing on the photo paper to see if an amount of hydrogen sulfide is present. So this field that's on the left side, you see it's mostly white. It should be completely white, but it's not tarnished. And then the exposed tarnish strip on the right has been placed outside. It's from a natural gas processing facility in Texas, and it indicates the hydrogen sulfide because it's darker. So as an indexical sign, the degree of tarnishing is both caused by and conveys the amount of hydrogen sulfide exposure over a given period of time. And we create the tool using photo paper, photo flow, glycerin, and make the strips, cut them, place them into film canisters, and set them out for 1 to 3 weeks. Then we fix the paper in a dark room and map them. So these tools are designed to be low cost at $1 per canister or less, and the procedures and materials are readily available as research notes on the DIY environmental science site publiclab.org. So we use this tool to characterize sources of gas across various landscapes, and we work with community members and organizers from nonprofit organizations such as Earthworks and Shale Test to develop the photo paper tool, decide where to place the samples, and then map the results. So the community members near oil and gas facilities, like these 2 families I met in Texas, are experiencing issues with their health that began shortly after oil and gas development started around their homes. So they know they're being exposed to hydrogen sulfide because of the rotten egg smell, and they can benefit from a tool that can visualize their exposure since the smell itself cannot be captured. They can use these results to communicate their exposures and then legitimize their experiences around oil and gas development. So we work with communities to map the exposures, and this is an example of a map around Wyoming. It's in a ranch, and it identifies one point source of hydrogen sulfide. And you can see that it is around the discharge canal where the hydrogen sulfide is coming out. So the darker strip, which is around the discharge canal, indicates higher levels of hydrogen sulfide, and as you travel away from it, there are lower levels. So here's another case, a larger scale study in Texas, where we're characterizing non-point sources. So you can see in this 6 by 8 kilometer area that there is a background, pretty consistent background level of hydrogen sulfide. And this is where the families in Texas live. So we can't pinpoint one source, but we can visualize the exposure to hydrogen sulfide across the whole area. Now, we're working on validating the results from the photo paper tool in order to legitimize this. In Texas, we co-located the photo paper with other hydrogen sulfide sensing tools like radialo tubes and corrosion coupons and placed them in these little bird houses, which are one's on exhibit in the back of the room, in order to sort of hide study from all the oil and gas people out in Texas. And we also use the industry standard Jerome meter. So we control for internal consistency with the field blanks and field duplicates. And since this is an indexical tool, we're working on analyzing the contents of the paper itself with an XRF gun. And the XRF gun shoots X-rays, which, and it's also back there, and I can show you during lunch how it works. It's calibrated to look at metals. And since the photo paper involves a reaction between the hydrogen sulfide and the silver, we can see from the silver how much hydrogen sulfide is present. So without hydrogen sulfide, most of the silver washes away during the fixing process. And I just ran this last night. You can see a screenshot of a field blank. The silver is non-detectable, you can see on the screen. And then with the tarnish strip, you can see that there's 42 parts per million of silver. Another tool that we're using to sort of prove this correlation between silver and sulfur is the XRD machine. And you can measure the amount of aggregate sulfur that reacted with the silver, and then see the correlation on the sulfur and silver. So we were really excited to see this really high correlation coefficient, or R value, at 0.97, and then the P level is less than 0.0001. And if you're familiar with statistics, this is pretty exciting. And it means that most of the amount of silver that we're using or seeing on the XRF most likely indicates that the level of hydrogen sulfide that's on the strip. So that's all I have for you today. And if you'd like to check everything out, it's in the back. We have maps and strips and canisters.